Hi everyone, I hope you're doing well. So today we're going to try a little bit of a new structure with the online stuff. So I'm going to try and make some short videos talking about some of the key concepts and examples from each section in the textbook. And then I'll ask you to look at some example problems during our live lectures. And so the goal for today and the coming classes is going to be to talk about sequences. And so a sequence is just a fancy name for any list of numbers. And because we're in calculus, we're often going to be interested in the long-term behavior of a sequence. And so in other words, we're thinking about limits of sequences. But to begin with, I just want to make sure that we're all clear on what a sequence is. And so a sequence, like I said, is a fancy name for a list of numbers, and we'll often use the notation for a sequence of bracket a sub n. And then each individual number in a sequence is called a term. And so there are many different examples that you could come up for a list of numbers, but let's look at a couple relatively basic ones here. And so the first one here, we're just looking at 1/2, and then 1/4, and then 1/8, and then so on. And so it's pretty clear that there's a pattern going on between the terms, and we'll talk about that more in a minute. Another example might be if we just have 1, 3, 5, 7, and so on. And so in other words, just all of the odd numbers. And another one might be just alternating between -1 and 1 repeatedly. And so even though the numbers here are repeated, that's okay. This is still a valid sequence. And so in order to be able to analyze the long-term behavior of a sequence, one of the key things we're going to want to be able to do is translate between a list of numbers and a formula. And so in other words, what I mean by that is I want to be able to figure out what the 100th term should be in any one of these sequences just by plugging in 100 into something. And so what I'm going to do is I'm going to view these sequences as having first term, a second term, and a third term corresponding to n being equal to 1, 2, 3, and then so on. And I want to be able to write a formula in terms of n so that if I plug in n equals 100, then I get the 100th term out in the sequence. And so we'll try and do that for these three examples right here. And so if we look at the first few terms in this first sequence, and so we have a sub 1 is equal to 1/2, a sub 2 is equal to 1/4, a sub 3 is equal to 1/8, and so on. And so this is just the notation we would use to convert this list into a's. Right here, I'm just saying the first a is 1/2, the second a is 1/4, and so on. Now, if I want to convert this into a formula in terms of n, then what I'm going to do is I'm going to start by looking at the pattern that happens between these consecutive terms. And I just want to think about what's happening to these numbers every time I move over one red arrow over to the next term. And for this one, you can see that the pattern here is that I'm just multiplying by 1/2 each time. And so now I need to figure out a way of representing that in terms of a formula. And so the idea should be that I'm really multiplying by 1/2 each time. That's the same as having a formula of 1/2 to the n. And so the reason for that is that this 2 to the n corresponds to multiplying by 1/2 each time. And so in other words, this multiplies by 1/2 when n increases by 1. And so this is capturing the behavior between the terms. And so the other thing that I need to think about is whether or not this formula gets the first term correct. Because overall, in order to get a correct formula for a sequence, I need to make sure it does the correct thing between terms, and then that it starts in the right spot. And so in order to check that, all I have to do is just plug in 1 into my formula. And so if I do that here, then I would just get 1/2 to the 1, which is equal to 1/2. And so that is correct in this problem because I do have that a1 should be equal to 1/2. And so for that reason, I'm done, and this is the correct formula for this sequence. Now, if we look at the next sequence, where we have a1 is equal to 1, a2 is equal to 3, a3 is equal to 5, and so on, I want to do the same sort of analysis, where first I'm going to look at what happens in between these consecutive terms. And so here you can see that in between each of these terms, I'm just adding by 2. And so now I need to think of an appropriate way to represent that in terms of n. And so I want this to be correct so that whenever I increase n by 1, then my formula increases by 2. And so the way to do that is to multiply 2 by n. And now you can see that whenever n increases by 1, this will capture the correct thing. And so this is the behavior between the terms. And so just like last time, that's the first half, and that's typically the hard part about finding these formulas for the sequences. But I still now have to check whether or not the first term in the sequence is correct. And so if I plug in 1 into this formula, I'm going to get 2 times 1, and that's equal to 2. And that's not quite correct in this case, because I needed it to start by 1. And so this is not a big deal at all. All I need to do is just subtract 1 from my formula, and that'll make sure that it starts in the correct spot. And this 1 doesn't depend on n, so it's not going to mess up the rest of the sequence. And so now I've made sure that the sequence starts in the right spot by adding this minus 1 to the end of my formula. And then I've also made sure that it does the right thing between terms because of that 2 times n thing out front. And so overall, that guarantees that this... Sorry about that. All right, and so now we'll look at one more sequence right here. And so this one, I'll write out the first few terms in that other notation again. So a sub 1, the first term is equal to minus 1. A sub 2 is equal to 1. A sub 3 is equal to minus 1, and so on. Again, I just want to think about what happens in between these terms. And so there's a couple ways that I could view this sequence, and actually any of them would be valid, but some of them will be more convenient to deal with than others. And so one viewpoint is that when I go in between these terms, first I'm adding 2 to get from minus 1 to 1, then I'm subtracting 2 to get back from 1 to minus 1, and then I add 2 again, and then I subtract 2, and then I add 2, and then I subtract 2. And that's certainly a valid pattern that you could represent in terms of a formula. But in this case, it'll actually be easier to view this slightly differently as multiplying by minus 1 each time. And so you could see to get from minus 1 to 1, you just multiply by minus 1. And then to get from 1 to minus 1, you multiply by minus 1. And you just keep on doing that same thing. And this is a slightly nicer version of what's going on here because the rule is always consistent between every term, instead of the other example I gave where it's sometimes plus 2 and sometimes minus 2, which means it's going to be a little harder to express, although again, you could do it. And so again then, I need to figure out a way of representing multiplying by minus 1 in terms of a function of n. But this is really similar to the first sequence that we looked at, in that this is just going to be a minus 1 to the n. So now that every time n increases by 1, I'm just multiplying what I had before by another minus 1. And so now I just have to check and make sure that this agrees with a sub 1. And so if I plug that in, then I get a sub 1 as minus 1 to the 1, which is just equal to minus 1, and that's correct in this case. And so that means that we don't have to do any more work for this. This was already the right answer, so there's no other adjustment that needs to be done. And so it's worth mentioning here that this particular sequence comes up quite a bit, and there's another way of representing it in terms of trig functions. And so this one maybe would have been a little weird to come up with on your own, but it's certainly valid, which is that a sub n is equal to cosine of n pi. And that's just because cosine of pi is equal to minus 1, cosine of 2 pi is equal to 1, cosine of 3 pi is equal to minus 1, and it just keeps on alternating like that. And so we'll see for this particular sequence and some other sequences that are closely related to it, that sometimes it's easier to represent it in terms of trig functions, and sometimes it's easier to represent it in terms of powers, and it just depends on the context. All right. So for the 3 examples that we just talked about, they were relatively simple in the sense that we actually were able to come up with formulas for the nth term of the sequence. That's actually pretty lucky, and in general, if you're given just an abstract sequence in the wild, you might not be able to do that. You might be able to, but you might not be able to. And so just to make sure that this is clear, for example, we could write out an expansion of pi. And so this is something that the textbook wrote about for this section. And then we could just take the digits of pi. So 3, 1, 4, 1, 5, and individually convert them into the terms of my sequence. And so I can have a sub 1 is equal to 3, a sub 2 is equal to 1, a sub 3 is equal to 4, a sub 4 is equal to 1, and so on. Right? And so that's definitely a sequence of numbers that's well defined, and it even is the case that if you wanted to figure out the millionth number, then you really could figure out the millionth decimal of pi and write down whatever the correct answer was. But there's no pattern between the digits here. And so that means that we're not going to be able to write a nice formula for a sub n. And so that means that this particular sequence would be a really hard one to analyze in the long run. But we're going to try and stay away from sequences like this, and because we really do care about the long-term behavior of the sequences that we look at, we'll focus on sequences where you actually can find a nice formula for the nth term of the sequence.